So hey everyone, wishing you all a very belated happy Diwali. So welcome back with a new video and first of all it's my first video here. So as a part of my DSA assignment from our lecturer from the university has given us assignment to do a YouTube video based on the given topic to each and every one, which is unique. And so the topic I received is adjacency list, its storage and its efficiency, how different search algorithms will work good for its efficiency. So let's look into that in this video. And once again, wishing you all a very happy and safe Diwali. Celebrate it well, celebrate it with your friends and family. So let's dive into our video and see what adjacency list is and how does it work well, and how does it store with it, and how does time complexity and space complexity of adjacency list works. How can we construct it? How can we do a program? How can we implement a Java program in it? And also just a brief discussion about graphs and adjacency matrix as well in this video.
In this video, we are going to see what adjacency list is and how efficient storage and search can be done and performed on adjacency list. And also it is important in data structures because exploring the advantages of adjacency list for data representation and data retrieval is also important. Now, as we all know, graph can be represented in two types. One is adjacency matrix and one is adjacency list. Now, adjacency matrix has its fair share of disadvantages, so it has adjacency list has been created or invented, and all the disadvantages adjacency matrix has can be overcome by adjacency list. And also to note that adjacency list also has its fair share of disadvantages. That all we are going to look into this video. Graphs are also just of two types: directed and undirected graphs. Directed and undirected. Now, what directed is and what undirected is. Undirected is nothing but where a specific direction from one node to another node is not mentioned. Directed graph is nothing but where a specific direction from one node to another node is mentioned with a small pointing arrow. Undirected is nothing but where it doesn't have any pointing arrow, because from one direction to another direction, from one state to another state, direction is not mentioned. So graph is represented by two types: adjacency matrix and list. Now, as we all know, adjacency matrix had its fair share of very disadvantages. So we are going to see the adjacency list. Now, the contents that we're going to cover in this video are nothing but introduction to adjacency list, construction of adjacency list, search algorithms on adjacency list, and how storage will affect its operations, and also the future direction, nothing but the real world applications that we are going to see. Now let's understand the basic terminology of all the things that comes under graphs. As we already discussed about directed and undirected, we already know. Weighted and unweighted graphs are nothing but if in the graph on the wedge, if the edge that has any distance or else cost specified, it comes under weighted graph. On the edges, if the graph has nothing specified, that means that it doesn't have any distance or cost specified on its edges. Those are called unweighted graphs. Vertex is nothing but this one, and vertex is nothing but the element or the point in the graph that is crucial for defining a structure. Edge is nothing but the link present between different vertices is called as an edge. So this is an edge, this is a vertex, this is a vertex. Now let's understand what an adjacency list is. Now the basic definition and basics of adjacency list is nothing but it is a way of representing a graph. Now what are the components that adjacency list has? Nothing but nodes or vertices come under the same thing, and different edges connecting one to one vertex is called as edge. Now, adjacency list for each node stores the connecting edges. Now, what are the comparisons that why adjacency list has been created? Because it stores the graphs with limited memory compared to adjacency matrices. Now, let's see how adjacency list can be created. Now, as we all discussed, graphs can be of two types: directed and undirected. Now, let's take 1, 2, 3. Now, as this is an undirected graph, now let's see how this graph can be stored in an adjacency list. Now, let's create an array that has all the vertices here, 1, 2, 3. Here are all the vertices. Now, this is an array of lists of list. Now, I'll tell you why this is called as array of list of lists. Now, there is a proper reason why it is called like this. Now, 1, as is an undirected graph, it is connected to both 2 and 3. Now, let us name here. Now, it is connected with the nodes here and it is mentioned with a null value. And now 2 is connected to both 1 and 3. Now let's mention that in the same nodes as well. As we know, the linked list is represented like this, where in in the address part, it stores the address of the next node. Now here it has the data, and here it stores the address of the next node. Like that will represent. Now 3 also has both 1 and 2. I forgot here null, so please do mention it. And even if you don't mention null there, you can mention it here. So let's erase the part. Let us erase this. You can mention null here. Now this is called array of lists because these are lists. These are called as lists. 2, 3, 1, 3, 1, 2. These are called as lists. Now this is an array that is storing the values of vertices as a list, which consists of different lists. This 2, 3 are called as different lists, and this 1, 2, 3 it is a list that which is stored in the format of array. So it is called as array of lists. Now let us understand how much space and time complexity this adjacency list storage is taking. Now this uh, stores order of v plus e because it stores all the vertices plus edges. Now vertices are 1, 2, 3. Now edges are 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 6 plus 3, 9. Now let us understand for the same graph how much space is adjacency matrix taking to store its values. Now in adjacency matrix we know we'll create 1, 2, 3, 1, 2, 3. If a 1 to 1, 0, 1 to 2, 1, 1 to 3, 1, 2 to 1, 1, sorry, 0, 1, 1, 1, 0. Now, the space this adjacency matrix is taking to store these values is order of v square. Now, 3 square, it is 9. Now, as this graph is a small graph, we are getting the same space complexity. Now, let us think if we extend this graph, let us see if we get the same thing or not. Now, here we have incremented it with 4 and 5. Now let us also increment with 4 and 5. Now 5 square is 25. Now if we increment this with 4 and 5, we'll get, now 4 is connected to 3. So 1, 3. Now 5 is connected to again only 3. So let us understand 5. This will change to 5. This will change to 5. And edges will be 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 5, 13. Now understand 25 will be more or 13 will be more. Obviously 25 is more. So adjacency list has a efficient memory storage. So we have gone from adjacency matrix to adjacency list. Now let us understand the importance that adjacency list has in data structures. As we already discussed, it has efficient memory storage compared to adjacency matrix because the number of adjacent vertices is stored is comparatively less than adjacency matrix. But it can also be used with large number of vertices also can be stored in adjacency list. It is best for representation of sparse graphs, and it also has performance advantages because searching can be easy. Searching will be easy if the space that it takes to store the graph will be less. Better performance in graph algorithms that rely on edge list. Now let us understand the practical applications. One is the network representation, nothing but different computer networks connected or one system to another system connected. It is the example. Social network analysis, I think, will be the best example to describe adjacency list. As we all know, we use Instagram in our day-to-day life. So there, as all of you know, we have friend requests. Now let us understand if one friend is trying to connect from one friend, a link will be created. Now, if the same friend is trying to remove a friend connection for another friend, the link will be removed so that the vertices will be present, but the edge connecting them will be removed. So, if you keep a friend request, an edge will be created. So, this social media networks or social media connections and all will be the best example to describe adjacency list and all. Now, dependency graphs in software engineering, nothing but we use different components of software engineering in our day-to-day life. The best thing that we use is build systems that to determine a component build order. So that is one of the also example, but I definitely suggest the social media example will be the best to understand adjacency list. Now let us understand how to construct an adjacency list. As we already know, first we have to initialize the list. We have seen here. Uh, we have seen here how different what array of lists are being created. So that's what we have to first initialize the list with the number of vertices that we have in the graph. As we have seen undirected graph, now let's understand about the directed graphs example here. So let us take the same example 1, 2, 3. Now, but with the direction specifying. So let us take this. Now from 1 we have both 2 and 3. Now from 2 we have nothing. So it will be null. From 3 we have 2. So this is an example of a directed graph representing an adjacency list. Now let us understand this order of v plus. Let's understand this time and space complexity. 3 plus edges is also 3, so 6. Now to search whether a vertex or an edge is present or not, that time now to search whether a vertex is present or not, it will take order of v. To search whether an edge is present or not, the space complexity it takes is order of e. Now whether it comes to adjacency matrix, it takes it takes order of 1. To search whether an edge or vertex is present or not, it takes order of 1, where this one case is a slight disadvantage that adjacency list has. But order of 1 it takes in adjacency matrix to search whether an edge or vertex is present. Whether it takes order of B or E respectively to search whether a vertex or edge is present or not. This is also best example in it's also adjacency list also can be used better for dynamic graph because we need to add edges and vertices continuously. We can also remove edge as per our requirement. Now, as we already discussed, array of different linked lists, now dictionary of lists, as we are mapping from one vertex to its edges, we are mapping it. So this is also called as dictionary. It can also be used in dictionary because in Python, generally dictionary to map from one vertex to edges, it's called like that. So not only in Java or C++, you can also execute it in Python. And also we're using efficient use of pointers because we're trying to represent from one edge to another edge. We are using pointers to travel also. So that is the best use in data structures. Now we also discussed adjacency list space complexity will be order of V plus E. And also order of E to search whether an vertex is present, order of E to search whether an edge is present or not. In the same way, in adjacency matrix, we get order of V square to store all that graph. Order of 1 to search whether an edge or vertex is present. Now, in this case, searching, it has a slight advantage of adjacency matrix than adjacency list. But it also, in adjacency list, it avoids redundancy. What is redundancy is nothing but the duplication. Adjacency list also prevents duplication here. Now, we have already discussed. Now, this is 1. This is order of P to search whether an edge is present and order of E to search whether an edge is present, order of B to search whether an vertex is present or not. Now, adjacency matrix is best for dense graphs as adjacency list is best for sparse graph. This point needs to be clearly noted. Now, different space complexity analysis of operations also we have discussed. Now, what definition of adjacency list is? It is a collection of lists of arrays and order of 1 for inserting an element. Now, travel cell BFS, DFS can be used, but DFS will be best because in DFS we get an option for back traversal or else nothing but backtracking in order if we specific specific clearly. Now, time complexity will be order of V in worst case to search whether a vertex is present or not, order of V plus E to search whether a vertex or edge is present. Now, different search algorithms on adjacency list, as we already discussed, BFS, DFS can be an option. In BFS, DFS, DFS is used because last in, first out data structure, and it also uses stack mechanism to allow DFS for back traversal in order to understand or in order for implementation example. Now, code implementation is provided how DFS can be executing. DFS, BFS both are fine, but DFS will be recommended because back traversal is given. BFS, we don't have option of back traversal, so we generally prefer depth first search. Now, limitations at adjacency list, as we also discussed in the starting, we have known that adjacency list also has its fair share of disadvantages. Not disadvantages, like we can put it as like limitations, nothing but inefficient for dense graphs. As we have seen, adjacency matrix will be best for dense graph and adjacency list will be best for sparse graph. This will be one of the inefficiency that dense graphs can be not be represented by adjacency list. And also we have discussed that adjacency list will be best for unweighted graphs. Now if an weighted graph comes into case, not telling that we can't do it with adjacency list, we can represent weighted graphs using adjacency list also. But as we have discussed, the space complexity will be order of V plus E for unweighted graphs. If we put another edge weighting constraint in the graph, the space complexity will increase. But yes, it will slightly complicate the problem because mentioning the distance or cost on the edges will increase not only the space complexity but also it will increase a little complexity of finding or searching any edge or not. So that is also alongside of adjacency list will also be a slight limitation, I suppose. Now advanced topics are nothing but weighted and directed graphs. Now see, adding weight attributes to the edges in the list will cause a little constraint, but maintaining a sorted adjacency list by weight will be a little constraint here. But also efficient storage methods for edge weights is also possible in adjacency list. Now we are also implementing directed graphs as we almost as we have seen this example. This is an example of directed graph, how adjacency list can be implemented from directed graphs. Now, challenges and solution is nothing but managing edge directions. Now, edge direction managing will become a little complex because if it is a small graph, it is fine. If we take a very big example that has edge directions and all, and also it has weighted, if it is a weighted graph, it will become a little complex and also takes some more time and space, but it can also be done using adjacency list. Now, dynamic graphs. Now, adjacency list will be the best for an dynamic graphs because here we can add the number of vertices easily in this array of lists, and we can also add different edges connecting it without disturbing the whole graph. We can add the number of vertices and edges as many as we like without disturbing the graph that is already constructed. Now, this is a major big problem that we faced in adjacency matrix because it is stored like in the form of number of vertices, it takes order of p square and all. Now, in order if we are trying to add new vertices or edges, we have to, as we are representing things as zero, if the edge is not present or if the vertex is not present. Now, in order to, if we want to add a new vertex or an edge, we have to remove this and we have to add new thing. Because of this removal and adding, the adjacency matrix is becoming very tough to represent dynamic graphs. Whereas when it comes to adjacency list, dynamic graphs can be very bestly represented with adjacency list because we can add the number of vertices so many as we need, and we can also add the number of edges connecting these vertices without disturbing the previous graph or else without removing anything. Even if I want to remove the connection edge between 2 and 3, I can remove it easily with removing the pointer, but the vertex will be present as it is, but just the connection here will be removed by just removing the pointer. So now I think hope you had a clarity because why adjacency list can be mostly preferred than adjacency matrix, because dynamic graph is also one of the thing that in generally we speak of dynamic graphs and static graphs, but dynamic graphs are very much important in our day-to-day life because we have no use or we can see no real applications of static graphs in our day-to-day life. So handling dynamic graph scenarios or insertion and deletion of nodes and also modifying adjacency lists dynamically, these three cases comes under handling or taking inputs dynamically. These three can be best suited or treated with adjacency lists. Now, real world applications, we have already discussed social media networks, nothing but Instagram. We have already talked how a friend request can be created and how it can be removed, but the vertex will be present and all. Now, internet routing protocols, nothing but border gateway protocol is one of the protocols that we have seen or we use in our day-to-day life that is very much needed for internet and all. That is also best application for adjacency list. And also transportation networks, nothing but the traffic flow in this modern cities. The traffic management is also become a very big thing. So adjacency list can also be utilized there. Now let us understand or develop a Java program on a graph using adjacency list representation. These are nothing but some importing some libraries. Now, adjacency public class adjacency list graph. This adjacency list graph is a class that needs to be followed camel case. whenever you are creating a class, make sure that you use camel case when you're defining or creating a new class. Now we have created also public static void main. We have taken scanner class that takes real-time inputs. It is asking for number of vertices. Now here we are giving number of vertices using scanner class to take real-time dynamic inputs, not taking values statically. And it also asks whether a graph is directed or not. If it is a directed graph, give true. If it is a not a directed graph, give false. Now here we are using tertiary operator because it helps, or also it also minimizes the constraint of the problem. Or it doesn't take much space if you use tertiary operator in this code. Now if it is a directed graph, we have to give true. If it is not a directed graph, give false. Now we have to create an adjacency list, that is nothing but array list of linked lists. It takes integer values. It also increments its vertices using a for loop. And it is also creating an array list that we have seen that all we can store all the vertices. Now this is called array of lists of lists. Now this part of code is creating this, and it's also using for loop to increment the number of vertices that is stored. Now here we are adding edges. It also takes number of edges to be added. It also creates a for loop, and it also asks the user to give the source and destination that one needs to go. If suppose one is going for 2 and 3, we have to specify that in the real time output, and it is also taking I plus 1, nothing but incrementing also in the same printing statement. It asks for source and destination. It adds the edges. If at all a graph is created, if you want to add more edges, now this part of the code helps us to do that. It is also we are taking this constraint because source and destination can't be given as it is. We have to see the graph and we have to give it all properly. Now, if the graph is directed, we have to get to add the destination and also the source. Now, everything is done. We have given all the constraints. Now, we have to display that adjacency list. To display the already given adjacency list, we need two for loops to print the number of vertices, to print the adjacency list and all. Now, let us see how the output is given. Now, it asks for number of vertices. We have given 4. If it is asking graph is directed or false, for this example, we taken it false. The number of edges we have taken 3. So for 1, the source and destination will be 0 and 1. For 2, 1, 2. For 3, 2, 3. Now the adjacency list will be printed like this. Now for 0 it is 1, for 1 it is 0 or 2, for 2 it is 1, 3, for 3 it is 2. Now that is the a very simple and small problem that also takes dynamic inputs, which is a very small problem compared to adjacency matrix or list. And it also is very much useful to implement real-time adjacency list through a Java program. That's it. Thank you, everyone. Next time we'll meet in a new video. I am Suveda. For today, bye-bye.